Log on, tune in, find out. Another good idea from Cambridge.
Thank you very much, and thank you very much for inviting me to take part in the program and to give a seminar, and thank you very much for coming to the seminar. I understand I'm in sort of dangerous position here because the seminar is scheduled to end at 12:30, so every minute I overrun by is a minute taken out of the lunch time, and therefore grievous injury. I shall try to sort of overrun by as little as possible. So, sort of derived McKay correspondence. I mean, if I want to talk about it, I'd better start by saying what is it. I mean, the formal definition is the direct category of the quotient stock is equivalent to the direct category of a crapping resolution. So kind of one big messy category is equal to another big messy category. What's the big deal? So let me kind of spend about 5 minutes in the beginning to relate it to some honest geometry. So I mean, the whole story started with classical McKay correspondence. And in this story we have G, a finite subgroup of SL2C. So it's one of the ADE groups, and we have a quotient space which is generally singular, and we have Y, which is the minimal resolution. Since we're in dimension 2, we have this luxury. So we have this picture. We have C2 with action of G on it. There is a quotient map to the singular quotient space, and then there is a resolution. So there was an observation by John McKay in about 1980. Who observed that two sets, one is set of non-trivial irreducible representations of the group. So non-trivial irreducible representations of G. So it's G set of irreducible representation minus the trivial one. And this set is in one-to-one correspondence with the set which I call Y, which is the set of irreducible exceptional divisors on the resolution. Well, to be slightly more precise, the observation was a bit more than just the correspondence of sets. I mean, it also observed that a certain bit more of structure and that coincided. So here we have McKay quiver, or sort of representation graph of G, which tells us if you take one irreducible representation at tensor by the given one, and then this tells you information about what other reducible representations are contained in that product. And over here we have intersection graph, which is just kind of information about how irreducible divisors intersect. And this coincided too. In fact, sort of the real observation by John McKay had nothing to do with these two sets being equal. He actually observed that this representation graph of the group is an affine, for every group is an Dinking diagram for one of the affine Lie algebras of AD type. And then he observed that this is the Dinking diagram for the finite dimensional Lie algebra of the same type. Hence this correspondence. So sort of, and John McKay mostly cared about the Dinking diagram thing. So if you take this thing and throw out the exact thing that John McKay was interested in, you obtain the classical McKay correspondence. So as an example, sort of, if you have your group, say, being cyclic group on 5 elements, then this set together with the McKay quiver looks like this. Sorry? Well, because it is an SL2, there's only sort of one way to for it to sit there, which is this. I mean, every other way is pretty much equivalent to this one. In SL3 and above, you could have a cyclic group sitting several different ways depending on the way the weights. So this means that you have a root of unity embedded into SL2 like this. Of course, so because you have you sit in SL means that this product is 1, which means that this sum is pretty much 5, and there's only sort of one real way for this to happen. So if these are characters of the group, with this being the trivial one, then this thing is take this sort of McKay quiver and throw out this. You're left with precisely sort of this little diagram and the resolution of the singularity. I mean, if this is sort of origin in the singular space, and these are sort of two hyperplanes, sort of x equals 0 and y equals 0, or well, to be more precise, x squared equals 0 and y squared equals 0, then what happens? So this is x squared equals 0, this is y squared equals 0. Then what happens when you blow up, you sort of insert 4 p1s running like this in here. And the intersection graph is precisely this. So this was just an observation. And the next question was, is there any sort of geometry lying behind this observation? Is there a sort of real geometrical correspondence going on? So we have then people thought about it and came up with it. So we have geometrical construction. So this correspondence is precisely what's known as classical McKay correspondence. So geometrical construction of classical McKay correspondence. This was due to Gonzalez, Sprindberg, and Verdier in 1983. So they sort of added a bit of structure to that little picture. By taking inside y cross C2 a subscheme Z, where Z is the reduced fiber product over the quotient singularity. Then inside Grothendieck ring of equivariant sheaves on y cross C2, they take the class of the structure sheaf of OZ. So structure sheaf of OZ lies in here. This is G invariant subscheme, therefore the structure sheaf is G invariant with respect to action of G on this guy. And you take, so this is Grothendieck ring, K theory. And then they have taken theta of E to be a, well, K-theoretic Fourier-Mukai transform from equivariant Grothendieck ring of C2 to kind of normal Grothendieck ring of Y. So this is sort of K-theoretic Fourier-Mukai transform. What this means is, I mean, like always when you have an object in diagonal, to get a transform from here to here, you take any class in C2, in G-equivariant Grothendieck ring of C2, you lift it up here, tensor it with the object which defines the transform, push it down, and take an invariant part of it, which is, because when you just push down, you end up in G-equivariant Grothendieck ring of Y, where deduction of G on Y is trivial, and you have to take the invariant part. So. I mean, the way to get rid of this taking G-equivariant part to make it transparent is to work with a smooth stock. then this is sort of this becomes the part of the Stucky push down. But anyways, so we have this, and then the main theorem of the paper asserts two facts. First one is that this is an isomorphism of abelian groups. So it is one-to-one, but it doesn't respect the ring structure. And more interestingly, for any non-trivial irreducible representation of G, if you take structure sheaf of the origin in C2 and twist it by rho and take its class in the G-equivariant Grothendieck ring of C2 and look at its transform, you will obtain precisely a class of some irreducible divisor, well, twisted by -1. I mean, they're all P1s, so this is kind of pretty well defined. So here by O0, I mean point sheaf at the origin of C2, and E rho is some element of irreducible exceptional divisor on Y. And moreover, correspondence rho goes to E rho. The reducible representation goes to the divisor which its transform is supported on, is a one-to-one correspondence between irreducible, non-trivial irreducible representations and exceptional divisors. And I mean, there is also a way to get this extra information out of this transform as well. So what lies kind of on top of this coincidence between irreducible representations and curves is the fact that the structure sheaf of this reduced fiber product defines a one-to-one correspondence between sort of K theory on Y and equivariant K theory on C2. I mean, this is just representation theory. This is where, so the slogan of the whole McKay correspondence from the start was that representation theory of G is the same as sort of geometry of the resolution. So anybody who works with derived categories sees this, and the next question is, does it lead to derived categories? Yes, it does, and in fact, this is what a derived McKay correspondence is, and that is how you generalize this to dimension 3. So, I mean, one immediate problem, if you ask how to do this in dimension 3, is that in dimension 3 we no longer have the luxury of having the unique minimal resolution. So the first question you ask yourself is, what is the scheme Y you should play this game on? And you can observe that in two-dimensional case, the minimal resolution can be thought of as G-equivariant Hilbert scheme of C2, which is kind of, we can think of it as G-equivariant part of the Hilbert scheme of n tuples of points where n is the order of the group. Or you can think of this as fine moduli space of G clusters, and I will explain what these are. So, right, let me write definition. So, a G cluster in Cn is G-equivariant subscheme of Cn well, Z of Cn such that its global sections, its range of regular functions, is just a regular representation of G. So any G equivariant, any free orbit is a G cluster. But if you've got a orbit with this, if you've got any point, any sort of degenerate orbit, any orbit with non-trivial stabilizers, then you need to thicken it up a bit. The size of the reduced subscheme supporting such orbit is smaller than this, and you need to take a thickening. And then the kind of the thing that kind of tells you that this is the point of view to take is that this Z defined there reduced fiber product is the universal family for this moduli problem. So now you have your answer as to what you should play this game in dimension 3 with. So
What is that notation tilde on your fiber?
oh, reduced fiber product. Sorry, this means kind of yeah, this sort of reduced fiber product. So the tilde means reduced. So theorem. Bridge on King Reed in 2000. So take any finite subgroup of SLN-C where n is 2 or 3, dimension 2 or dimension 3. Take y to be G cube of Cn, define moduli space of G clusters. Take Z on y cross Cn to be universal family for this, for the G cluster moduli problem. And let dy be the derived category, bounded derived category of coherent sheaves on Y. And let dg Cn be bounded derived category of G equivariant coherent sheaves. So we have pictures before. We have y cross Cn, we have y Cn and the fiber product, and the kind of quotient space, and then we have an object in here, and we take E to be simply the class of the structure sheaf OZ again in the derived category of the product. The theorem asserts that Fourier-Mukai transform defined by E once again, but this time it goes from Y to, and that's the kind of the whole point of the approach, from Y to Cn, but as before, take an object in derived category here, pull it up, tensor it with E, push it down. So this is an equivalence of categories. Consequently, as a kind of immediate consequence of the fact that these two categories are equivalent, Y is a cracked resolution of C and So crepant means that the pullback of the canonical class of the singularity is the canonical class of your resolution. That's the formal definition. Another way to think about it, that we know that if you consider all possible divisors as sort of valuations in a function field, then you can talk about them being crepant and discrepant, or discrepant. And the kind of crepant resolutions, somehow minimal resolutions. They're resolutions which contain only the crepant divisors. If you have, there can be several of them. You have the same sort of crepant divisors, only sort of intersecting in a different way. But if you've got any resolution, it must in particular contain all the crepant divisors. It's kind of particularly well seen in the toric picture if you look at the quotients by billion groups. But the basic idea is that once you know that this is equivalent, then in particular, sort of any object here has finite homological dimension and can be every object in here is perfect. Therefore, every object in here is perfect. Therefore, every point sheaf has finite resolution by locally free sheaves. Therefore, this is smooth. And the crepancy is obtained from the fact that this has a trivial self-functor. So this is just sort of standard derived category logic. So then you notice that the whole thing is actually a bit more general than that. I mean, pretty much the same proofs without any change go through for when you take y to be not G Hilb, but a solution to a slightly more general moduli problem. You take it to be m theta, the fine moduli space of G constellations. And let me define this. Of, theta stable G constellations. So, and you take E to be universal family in which is a coherent sheaf on Y cross Cn, G equivariant 1 flat over Y such that every fiber is a G constellation. So let me define what a G constellation is. A G constellation is a coherent sheaf F so to be more precise, it's a G equivariant coherent sheaf on Cn. Such that its global sections are isomorphic to a regular representation, the regular representation of G. So, in particular, a structure sheaf of every G cluster is a G constellation. Another point, sort of, I don't want to talk too much about theta stability, but the idea is that, in fact, G constellations are just representations of the McKay quiver with a certain fixed dimension vector. You have kind of theta stability, Alistair-King's theta stability for representations of quivers. I think it was mentioned last week during the lectures. And this theta stability for G constellation just says that G constellation is stable, the corresponding representation of the quiver is stable. And in fact, so G clusters are precisely G constellations stable with respect to a certain distinguished stability condition. What is asserted here is that if you take any other generic, if you take any other generic theta stability condition and the universal family for it, you can play the same game and the Fourier-McKay transform will give you an equivalence. And moreover, there is a result by Crow and Ishii, which is when this becomes really interesting, in 2002, which says that all projective creepant resolutions of C3 over G are obtained this way for G abelian. So then it's sort of natural to make a following conjecture. For every finite subgroup of SLN C, completely generally, and for any creepant resolution, the quotient singularity, we have this equivalence of derived categories. So this is what's known as the derived McKay correspondence conjecture. Then, if you have this, then you can take projections to K-theory, and in fact you will get the K-theoretic McKay correspondence. Then you can take a point sheaf of any singularity twisted by representations of the group, see where it gets transformed by, and get a real geometric correspondence between the representations of the group and subschemes of the exceptional set of Y. Already in dimension 3 it gives you a pretty interesting picture. There are less exceptional divisors than representations. So if you look where representations go under this correspondence, you see all exceptional divisors, you see some exceptional curves, you see some chains of divisors. It's a sort of, there is a rich geometrical picture to be extracted out of this, but well, first it would be good to prove this. So in dimensions, so that's the sort of reason for the name of this talk. In dimensions 2 and 3 it has been settled by BKR, and settled in a very nice way, which says that here is a scheme, G-Hilp C3. It happens to be a creepant resolution, and its derived category is equivalent to Y. Because the BKR first proves derived category equivalence, and then kind of this tells you that G-Hilp, or more generally any moduli space of theta stable G constellations, is creepant resolution. In dimension 4, creepant resolutions don't always exist, and G-Hilp is often either singular or discrepant, or for example, there are examples of G-Hilp singular in dimension 4. There are also examples where G-Hilp is a resolution, but it's discrepant. So you sort of don't have a chance of this holding. And there are two ways you can sort of go from here. One is if you're interested in this, in this particular kind of, in getting this equivalence. Then what I'm just about to describe now, which is a refinement of BKR approach, is not sort of your way. There is a nicer way to go, and if I have time at the end, I'll mention it. The other possibility is if you're interested in creepant resolutions. So your question is, suppose we have a group for which I know that creepant resolutions exist. How can I sort of get this method? How can I construct them using this moduli approach? And that's sort of what I'll talk about, because the mantra of BKR is that BKR does not work in dimension 4 and above. There is a sort of, and the proof really kind of fails, and I'll show why. But there is a sort of way to refine the technique they use to get it to work, provided you have some more kind of for some more special groups. So that's kind of, let me briefly outline the BKR approach to proving this equivalence, but in a sort of more abstract way, which lifts to higher dimensions. So suppose we have a finite subgroup of SLN C. And suppose we have any scheme which is, well, separated, irreducible, finite type over C. Suppose we want, we make no further assumptions about that scheme, but we want its direct category to be equivalent to direct category of C. And as before, suppose we want some object in the direct category of Y cross Cn to define an equivalence between these two direct categories. So what I call BKR approach is a sort of search for such object on the diagonal, or not on the diagonal, on the product of Y and Cn. You see. But suppose you also wanted to sort of be even vaguely geometric. I mean, you don't want to take, in any moduli problem, such functor, in particular in sort of BKR and its generalizations, if you take any point of Y, you will obtain at worst a G constellation here, which is a coherent sheaf on Cn with a certain structure. And that's sort of what I mean by being geometrical. The second condition I'm going to impose is I'm going to say that I want for any point Y on Y, the sort of derived categoritic fiber of E at Y, which is kind of just the same thing as the image of point sheaf of Y under this Derived McKay transform, is a sheaf in GCN. So by saying that it's a sheaf, I mean it's not a complex. It's an object which has single cohomology in degree 0. So that's certainly kind of covers any equivalence that.
You don't demand it's a quotient of the structure.
Sorry?
You don't demand it's a quotient of
No,
the
no,
structure.
no, no. I just have. If I just have that, then any such E in fact, when a G constellation already is not a factor, is not a quotient sheaf of the structure sheaf. That's the whole point somehow. You allow things which are not generated by one. So any such E is what's known as a Gnat family. So it's a family of G constellations, but a kind of slightly special one. Let me define what this means. So that's sort of any object which is likely to give you such an equivalence, where points go to sheaves, is a family of G constellations. That's the whole point to kind of for bothering with this object. So definition: a Gnat family. Well, I should be Gnat because it's G natural. Well, also because sort of better mathematicians than me introduced elephants into mathematics, and I start small. So a Gnat family is a flat family of G constellations over Y, so it's a sheaf on Y cross Cm G equivariant whose fiber over every point of Y is a G constellation, but we impose extra conditions which are each supported on a single orbit of G. It is perfectly plausible to have one of these G constellations which, despite having just the right length, or regular representation of G, is actually supported on two orbits of the group. So here we kind of chuck that out. Another way of saying the same thing is we have a well-defined Hilbert-Chow map. Every point of Y corresponds to some G constellations in a family. Every constellation corresponds to a unique orbit and therefore to a unique point in Cn over G. We get a map into Cn over G. There is a little easy proposition saying it's actually a morphism. So this fact continued, we don't just know that any E which defines the derived McKay equivalence is a knot family. We also know that continued. Hilbert-Chow morphism. Hilbert-Chow map from Y to Cn over G, which sends any point of Y to the support of the corresponding G constellation, is a crescent resolution of Cn over G. So any scheme which supports such fantastic family is a crescent resolution by default. That's pretty much what I said about Serre functions being trivial and the homological dimension being finite of all objects and so on. And also, we know a little bit about the family. Our family satisfies following nice properties. Gx between any two distinct G constellations in a family are all zero for all I and z, and when y1 is not equals to y2. So this is orthogonality in all degrees.
Excuse me, I'm confused.
Just a second. I'll finish writing and I'll happily. Yeah.
Why are these supports flat?
Why this supports what?
Varies flatly.
Why is what?
When you have flat family of G-parent sheaves
Yes.
of the kind you want, their schematic support, does it vary flatly?
Yeah, but look, I don't, no, not at all. The schematic supports are not flat at all, because you will have, over some points you'll have a free orbit, over another point you'll have just a single point. But the point is, it's flat as a family as a family of finite length sheaves. And here I just consider a map. This map is certainly kind of doesn't possess anything in the way of a property, of nice properties. There is a proposition which says that just this set theoretic map is actually a morphism. And then there's kind of a simple trick saying that it's a crescent resolution. So what sort of, there is absolutely no reason for the scheme theoretic supports to be flat over the thing. So the G constellations in a family would have properties that any two distinct ones are orthogonal in all degrees. Something is orthogonal in degree k if its kth x vanishes between them. Then we also know that, well, Gx0 is just G home from any G constellations into itself is just a copy of C. So this means that all the objects in the family are simple, and Kadeira-Spencer map, which sends a tangent space of any point y on y to infinitesimal deformations of the objects in the family along the tangent direction, is an isomorphism for all y in y. So let me call this sort of properties, kind of mark them by star. I mean, this should sort of speak more strongly that that you know, we don't just have a family of G constellations, we have a family of G constellations stable kind of solution of some moduli problem. In fact, just these things, there's sort of trivial moduli problem which says, let us take fine moduli space of all G constellations which occur in this family. Then what this says that Y is the fine moduli space for this problem, and E is the universal family. There are counterexamples where I mean, you might think that this tells you that the family is that there should be some stability theta for which the family is stable. However, there are counterexamples. There are crescent resolutions which are non-projective of the singularity. Families of G constellations which define the Fourier-Mukai thing is an equivalence, and therefore which have all its properties, and yet they're not theta stable for any given theta. So there's this sort of just theta stability is a bit too small to cover all the nice moduli problems on these things. But the nice thing about this is that also now this is a bit stronger than what you get out of a moduli problem, and this is stronger precisely because in a moduli problem you know that first Holmes vanish between the objects. Here we have all x vanishing between the objects, and in fact there is a very, very general technique which says that if you have something like this, any family which satisfies these properties would define an equivalence, so there's a converse. And essentially, so bridging king grid is all about sort of exploiting that.
So in the examples where these do not come from theta stability, do you have theta stability that includes those and other objects?
No, that's impossible because no, not at all. Because any theta, it's modular. I mean, the example there's example in dimension 3. Moduli space of any theta stable things will be A Krapin resolution, B projective Krapin resolution. The family which has been constructed exists on a non-projective Krapin resolution, therefore it could not possibly be include all theta stable things for some theta, because that would already give you kind of a nice moduli problem. So, conversely, let E be any natural family on Y satisfying then the Fourier-Mukai transform is an equivalence. From Y to BGCN. Now, this is not very difficult to prove. I mean, essentially you exploit the fact that because you have an equivalence, all these objects must behave like point objects, and then, you know, the only interesting thing is reduction to having finite length shifts and G cancellations, but that's also not too hard. This, however, is hard, but fortunately it's been done, and as I mentioned, it's an example of a much more general method which works for an arbitrary object in derived category about which you know that its transforms of point sheaves are sufficiently nice. This is sort of Bondel-Orlov technique which appeared in their paper called Semi-Orthogonal Decomposition of Algebraic Varieties. And the idea is that, as I will show in a second, the hard thing is to prove that, yeah.
You need to worry about the higher x between EY to itself?
No, that's kind of, you will see why not. It will be a part of this. So the idea here is that, firstly, the hard thing, I mean, Bondel and Orlov were worried about criterion for fully faithfulness. And in fact, once we show that this is fully faithful, it will immediately be equivalence for the following reason. A Fourier-Mukai transform has a left touch on it. This has a trivial Serre functor. A fully faithful embedding which has an adjoint defines the same orthogonal decomposition of this thing. Because the Serre functor is trivial, it becomes fully orthogonal. But Cn is connected. Its derived category is indecomposable. Therefore, the semi-orthogonal complement of the image of this is 0, and this is the whole thing. I'll write it out on the board in a moment. But the main thing is to get sort of the fully faithfulness is the hard thing this way. So, and all these proofs work like this. You take an object in the derived category of y cross y, which defines Fourier-Mukai transform isomorphic to the composition of the functor of your Fourier-Mukai transform, which you want to prove to be fully faithful, with its left adjoint. So this is the functor from dy cross dy. Therefore, we want an object on diagonal which defines the Fourier-Mukai transform. Well, this is the Fourier-Mukai transform. Its left adjoint is also a Fourier-Mukai transform thanks to Grothendieck duality. Composition of two Fourier-Mukai transforms is a Fourier-Mukai transform. It's sort of a standard little arithmetic. So let's have a nice object like that. And our goal will be simply to prove that it's a diagonal. The moment we prove it's a diagonal, then we've shown that it's actually an identity, and therefore, by kind of standard category theory, this is fully faithful. So, step 1. Claim that Q is a shift, so it's not a priori, it's some nasty complex. First step, it's a shift supported on the diagonal. So by capital delta, I mean the diagonal, the y diagonal embedded into its cross product with itself. So the main thing we use, I mean, this kind of the whole point of all this worrying about what your x's are become clear when the moment you see that, I mean, when you write out what Q is, then you can easily calculate that the gxi, ith gx between two G constellations is simply ith left derived pullback to the point y1, y2 in y cross y of this object Q. So by iota y1, y2, I mean spec C, a point embedded into y cross y, and the point, of course, is y1, y2. So you take any point in y cross y, you take direct pullback of Q to it. Its cohomologies are precisely ith gx between the corresponding G constellations. So therefore, in particular, y1, y2 lying in the support of Q means that some gx doesn't vanish. Well, if they all vanish, then the direct pullback to that point is 0, and therefore the kind of this doesn't lie in the support. So, in particular, orthogonality in all degrees, the fact that all x's between two distinct points, between two distinct G constellations vanish, immediately tells us that as an object in derived category, the support of Q lies inside the diagonal. So orthogonality in all degrees implies immediately that support of Q lies within diagonal. But we want it to be pure shift, and that's essential. And to get Q being a shift, we show that all its cohomology shifts except the 0th one are 0, and we do this via spectral sequence, which computes whose minus pqth term is pth left derived pullback to y1, y2 of qth cohomology shift of Q, pardon me for the small q and capital Q. And this converges to p minus qth derived pullback of Q. I mean, we use a bit more information here then, and let me sort of, I don't like giving spectral sequence arguments during talks, but this one is sort of really easy in a sense. Let this be Q max, so maximal, so max Q such that So maximal degree in which the cohomology sheaf of Q is not 0. And this be Q min. So this is minimal Q, such that cohomology sheaf of Q is not 0. Is not 0, sorry. And this is 0. And this line here will be codimension of this Q min here of Q. The main idea is here that we know that because this is gx p minus q's gx from ey1 to ey2, and these things are sheaves, in fact they're G constellations on Cn. Therefore this is 0 unless p minus q lies within the interval from 0 to n. And this is what really does it for you. And this is why it's important for this object to be sheaves. Because in particular, all stuff outside this thing vanishes. There are no terms here. It's kind of pretty easy to see. So in particular, this point, which has coordinates 0 q max, survives in the spectral sequence. This means that 0 minus q max is in the interval between 0 and n. Because if something survives in spectral sequence, this pullback is not 0, and then this has to lie inside this interval. In particular, this means that q max is less than 0. And the really beautiful part of this spectral argument happens in this point. Because the idea is that we have nothing here. So this point can only be killed by something that lies over here. This direction is the direction which you increase the order of the derived pullback. This is like L0, L1, L2, L3, L4 of respective cohomology sheaf. The thing is that, right, how should I do this? Oh. Let me write down a fact. I mean, the reason I go into this is because this is where this uses a crucial fact that then BKR uses a cut-down version of later on in its argument, which is the intersection theorem in commutative algebra, which is a pretty powerful tool, well, and many other reasons, implies the following thing, that if you have for any coherent sheaf on a variety, on a kind of sufficiently reasonable scheme, for any coherent sheaf F on a scheme X, and for any irreducible component of its support, and for any generic point, for any x in C generic, or rather kind of what I'm just about to say will hold restricted to the local ring of the generic point of this irreducible component. The following thing is true. I pull back to that point of F is not 0 if and only if I belongs in the interval from 0 to the codimension of C. So the idea, I mean, what this describes is simply the following thing. The bigger you go here, the bigger codimension of the sheaf must be. Suppose something kills us in here, then any point which lies in here survives in a derived pullback whose degree is higher than this. Therefore, the codimension of the irreducible component of the support of the correspective sheaf that it lies on.
Excuse me, you also on associated points, right?
Sorry?
Not just codimension of support, you on the
Look,
associated primes as well?
look, I'm talking about, in this statement, I'm talking about generic point or generic closed point
There
on.
may be embedded components in this.
I don't want to go into this at the moment. This kind of. But the main idea is that any points here have to lie on the components whose codimension is higher than the codimension of this sheaf. Therefore, all these points could not possibly cover the support of this sheaf. Therefore, in the support of the sheaf, there is a point where everything here vanishes. This point survives in this, giving us Q mean more than 0. And then, therefore, Q max is equals to Q mean is equals to 0, and therefore, and this pretty much means that only H0 of Q is not 0. So this, and then this does it for you, because then kind of you obtain that Q is a pure sheaf on the diagonal, and then it's this will answer the question about what happens about why do we not care about higher x of pointing to itself. So step 2. Now that we've shown that it's a sheaf line on the diagonal, we actually claim that Q is equals to struct sheaf of the diagonal. And the idea is that we consider the natural morphism from Q to O of the diagonal, which induces the adjunction co-unit. So this is surjective. It is surjective because for any y and y, if you take just normal pullbacks of these shifts to y, y, you will obtain precisely a map from 0 gx from EY into itself into home 0 from O, from the struct sheaf of a point into itself. And this is C, and just the sort of scalar multiplication and the morphisms of EY into itself will cover all of this. So this is surjective. So let K be the kernel of this. So we have short exact sequence from this into Q into O of the diagonal. And then we write long exact sequence associated now to the full derived pullback here. And it looks like this. We have this sort of starts us off from 0 from OY into itself, then zeros everywhere else. This is C into GX, G homes from EY into itself. Then we have our kernel, or rather its pullback. Then we have dual tangent space, dual of the tangent space of y at y, of large y, small y. I mean, we are pulling back this object. The pullback of this to y to point y is exactly this. And then, why do I always run out of space at this point? And then in here we have gx1 of ey into ey. I mean, this is the dual of the Kadara-Spencer map. So this is the dual of the Kadara-Spencer map. Therefore, if this thing is just a copy of C, then because it's surjective with no contribution from here, and if Canaris-Spencer map is isomorphism, this ensures that this is 0. And if the pullback of K is 0 to every point in its support is 0, even the first pullback, then the whole thing is 0. So Gx 0 EY plus Ks Canaris-Spencer map being isomorphism implies K is 0. So if you have this simplicity and Canaris-Spencer map being an isomorphism, which you have in any Moduli property, this comes for free. And then the third step I don't really have time to mention is the step where you claim that because you're fully faithful, you're equivalent. So so step 3, claim and the argument here is that as theta E has the adjunct, there exists semi-orthogonal decomposition of dg_Cn into image of theta E and kernel of its left adjunct as dg_Cn has trivial self-functor. So semi-orthogonal means there are no homes going one way, because we have a trivial self-functor. This means there are no homes going other way either. So this is fully orthogonal. And but dg_Cn is indecomposable. Therefore, this is 0. So I think if I'm allowed to, I would take up 10 more minutes of your time. So the advantage of going to the detail of that tells you what BKR does, because BKR, they have a moduli space. So they have simplicity, orthogonality in degree 0, and Canaris-Spencer map being an iser for every point in Y. So the thing they're lacking is orthogonality in higher degrees. So this very quick so what sort of steps 2 and 3 are okay, but we have a problem with step 1. So BKR replaces step 1 by the following argument. And in fact, in step 1, the spectral sequence still works. But you have a problem because you no longer have an argument that this is at least length n, because unless you know that the support of Q lies within the diagonal, this distance here could be less than n, and then you're in trouble. So what breaks down is the very first thing, because we have orthogonality in all degrees, support of Q lies within the diagonal. But then what they say is, it's a very quick argument. Work on y cross y minus diagonal. Intersection theorem can be worked not just for sheaves, but for any object in derived category. And for that, it has a following form. Tor amplitude of Q is more or equals than codimension of the support of Q. Tor amplitude is the sort of over every point of y cross y, you take derived pullbacks, and then you take supremo of all the degrees and infimo of all the degrees in which these pullbacks don't vanish. So it's sort of highest separation of degrees in which derived pullbacks to points do not vanish. And this is logical codimension of the support of Q. So and that's true for any Q in derived category of any reasonable variety. So if you're dealing with sheaves, then you have a statement, much more precise statement, that if you kind of are careful with your, if you go irreducible component by irreducible component through the support of Q, then this thing is precisely the dimension of irreducible component you are on. But you can be really crude and just do it like this, and kind of do all the irreducible components at once, and then not care that you lose equality. Well, that's fine. Because we have orthogonality in degree 0, we know that gx0 of any two G constellations, which are distinct in a feather. And therefore, by third duality, also nth gx vanish. But this means that Tor amplitude of Q is less than n minus 2, because all these x's vanish for I outside the integral from 0 to n, because these are sheaves in CN, and they also vanish here. So Tor amplitude is locked into interval from 1 to n minus 1, so it's n minus 2 at most. On the other hand, support of Q is supported on, lies within the fiber product, which is y with itself over the singularity. And that is because if two G constellations are supported on distinct orbits of G, they're supported on disjoint orbits, and all x between them vanish. But this, so if codimension of y cross Cn over Gy in the whole fiber product is more than n minus 1, then we have a contradiction, because this is meant to be bigger than this, and this is just me saying that this is precisely bigger than this, therefore contradiction. But we started by saying that we work on y minus the diagonal. So Q is 0 on y cross y minus diagonal. Therefore, support of Q lies inside the diagonal, and then the proof goes on just as before. So the crucial thing is this. But let's see, what does that say? In dimensions 2 and 3, this says that the codimension, well, is either 1 or 2. And for general resolution, whose fibers are divisors, this codimension will be exactly 2. So if the fibers of y are divisors, then the codimension of this is precisely 2 in y cross y. So in higher dimensions, if you have a dimension 4 or above, if there is any fiber of y which is a divisor, then this fiber product over the singularity will have codimension 2, and therefore it will not be bigger than n minus 1. So this, unfortunately, if y has exceptional divisors, codimension of y cross over y for Cn over G is 2, which is not more than strictly less than n minus 1 if n is 4 or more. So, and that's sort of why BKR doesn't work in dimension 4. But the idea is that if you go back to this spectral argument, sequence argument, you can be really careful here. Instead of taking the whole thing, you can start going component by component through the support of this, and notice that the bigger is codimension of your component, the less you have to prove. The more kind of the less vanishing you have to know, and this pretty much allows for the following generalization. I think I'll write that and stop. So sort of. Careful argument with the original spectral sequence. So once again, Y is scheme, separated through irreducible of finite type. E, a Gnat family. G-natural family. Then let's have sets which denote precisely the locus of all the points outside the diagonal where the gx's of order k do not vanish. Are not zero. And let's take closure. So this is sort of locus of degree k non-orthogonality. If we know that codimension of mk is bigger than n minus 2k plus 1 for all k in the kind of between 0 and n plus 1 over 2. So for first half the case, you know that this inequality holds. In comparison, BKR asks for the codimension of mk to be bigger than n minus 1 for all k more than 0. So you do more careful sort of accounting for this. Then we have an equivalence. The amazing thing here is that we do not ask anything about simplicity or anything about Kaderer-Spencer map. We do not assume our E comes from a moduli problem. So there's sort of a trick here, and the trick is in that step too, because actually it's easy to show that any Gnat family, when restricted to the free orbit locus, is just the free orbit. And anything like this will automatically have this property, the Kaderer-Spencer map being isomorphism, any free orbit is of course simple and so on. So on an open set within the diagonal, k vanishes. And then we have exactly the same argument showing that it's 0. It has got a codimension which is n plus 1, but its homological dimension is at most n, because you know it's a kernel of two things whose x's are locked in between 0 and n, and therefore it has to vanish. So the argument, what allows us to get rid of any assumptions on kind of Kaderer-Spencer being isomorphism or simplicity, is that we know what happens on a large open set which contains all the free orbits. And therefore, in particular, in dimension 4, this reduces to gx vanishing, gx1, just first x vanishing for any general pair of points in the exceptional set of y. So if you take exceptional set of y cross exceptional set of y, any pair of points on the exceptional set, and if you kind of take an open set within that, if you can show vanishing of first x, you've got yourself a Krappin resolution and the derived McKay equivalence. So, sorry for kind of overrunning.
Any questions?
So what are examples where this one?
Examples, right, so Miles Reed has a student who is doing this kind of calculations for dimensions 4 at the moment. She singled out a number of groups, of abelian groups for which G-Hill is a correct resolution. So now, next interesting thing, and in that case, this holds. So the interesting thing now would be to, I mean, the whole point of this approach is to now understand what group theoretic properties of G might imply this vanishing. Because the moment we have that, we can say for all the groups which satisfy this property, for all the finite subgroups of SL4, G-Hill with a correct resolution. So the answer will be probably published in the paper quite soon.
If there are no further questions, can we thank the speaker?